Great. Thank you very much. Thanks for the invitation to this great meeting. I would echo what Vera said this morning. It's a very nice, broad audience where it's not just a bunch of talks about the same thing, but very different things that are interconnected in nice ways. So it's been a real pleasure. So I'm going to continue the super story here. So I'm going to be talking about support varieties for Lie superalgebras in positive characteristic, unlike what Vera was doing. The thing on the bottom here, so I just moved 2 weeks ago to Oregon State, and so some OSU student had made this. The youth in the audience seem to know that this is something called anamorphs, which is new to me, but I thought it was pretty funny. As I was telling Eric, so I went to Corvallis to be the department head, and somehow this is like the evolution from being a grad student to becoming department head is somehow reflected in this as well. But
I'd say when you get to university president, maybe you're below the line.
Okay. All right, so yeah, so this is kind of just mostly a survey talk because there's lots of things we kind of understand, but lots of things we don't. One of the things I'd like to thank the organizers for is I have a bunch of questions in here of things we don't know how to do, and Pavel has promised to answer them all this afternoon, so I'm looking forward to that. All right, so throughout this talk, we're going to be looking at over an algebraically closed field, and basically all the results will be stuff that was joint with Chris at various times. And so very, very generally, like the kind of stuff you would have seen like in Kent's talk earlier this week is, if we have a symmetric monoidal category, you'd like to have some kind of useful invariants that tell you information about the representations, or maybe in Eric's talk as well. And so, for example, we learned from Descartes that if you have algebra problems, you should turn them into geometry problems, right? And think qualitatively. And so that's what a support variety theory does, is given some object, associate to it some kind of a variety which has some nice properties. And Vera already talked about this a bit this morning, but the kind of things that you kind of hope for, I guess I'm supposed to use my pointer here, is that like direct sums in the category should be reflected as unions in your variety theory. And she didn't mention this, but you should have this kind of 2 and 3 property, which if you have some sort of an exact sequence, that the variety of one should be contained in the union of the other two. Some of these kind of often come out as kind of formal nonsense, and they're not too impressive. The harder ones, which is why I've marked these out with dots, are if you have the tensor product property. I think Sarah talked about earlier this week that this can be hard and subtle. And so you would like to have that, but it may or may not be true. You would like to have this detecting of triviality or projectivity somehow. Vera talked about this morning, and these mock injectives that Eric was talking about as well. You'd like your variety to tell you when they vanish, those objects should be sort of negligible in some sense. Oftentimes they're projective, but it might be something else, mock injective or something like that. And then another thing which Vera suggested she was going to tell us about, but then definitely did not, was realizability. So if you've got some kind of a closed set, can you realize that closed set as the variety of something? Okay. And so all 3 of these tend to be on the hard end of the spectrum of problems. If we're doing the general theory, Balmer kind of told us 20 years ago, which is, I'm old enough that that's not classical. If you have a tensor triangulated category, symmetric tensor triangulated category, then you can basically just copy over the definitions from commutative ring theory. You can define what a prime ideal is in this triangulated category. You can talk about the spectrum, and you just use the tensor product as you would do a multiplication and define the theory as you expect. And then for every object, you can define a support that's down here at the very bottom, where you just take all of the prime ideals that don't contain that object. And he showed that this is a really beautiful theory, and they've done tons of great stuff with it since. There's kind of a whole industry now. In particular, he proved that it's universal in a certain sense, in the sense that if you have some sort of a topological space and some kind of support variety theory which takes values, gives you subsets of S, like for every object you're getting a closed subset of S, and if it has some of those nice properties, then you will have a continuous function from that space S into this Balmer spectrum, and the supports will be related to it as well. So his theory is really sort of universal in this sense. So it's sort of the ultimate theory. Of course, if you live in the high altitude of the Swiss Alps and you're using this definition, like actually computing anything can be kind of hard. Like, what is it actually for an actual object? That kind of thing, because it's so sort of abstract. At least I don't know how to do it. You can ask Ken to calculate for you and put him to work. One other bit of evidence that this is a useful thing to look at is it classifies the thick tensor ideals in your tensor triangulated category. So thick tensor ideals means it's closed under direct sums and summands, and that it's closed under tensoring by anything in the category. And so roughly speaking, I think of this as, for example, what would be the thick tensor ideal generated by a single object? You're asking yourself, with that single object, what can I make by doing tensor products, direct summands, doing shifts, because it's a triangulated category. And this 2 and 3 property, if you have 2 of the things in there, you should be able to get the third one. So basically, all your basic operations, what can you make with that starting generating object or collection of generating objects? And so really, what this is telling you then is that the geometry of the spectrum and the support variety theory is telling you something sort of structural about how modules, or I think modules, can be put together in this category. Okay. All right. Now, of course, as I sort of said, this is all beautiful, and you can do lots of interesting things with it, but I'm a simple mathematician like Chris, and I want something a little more concrete. So if I have an interesting symmetric monoidal category, can we define some sort of interesting concrete variety theory? Maybe we could even get Balmer's theory, but maybe something short of that, but something more concrete that I can actually work with. The sort of most concrete version is the stuff that Vera was talking about this morning, where you can define things in terms of rank varieties, where you actually restrict down to single elements and talk about projectivity or freeness or some other kind of a property like that. And then it's really basically a linear algebra problem. You can actually calculate for a given module, is this element in there or is it not? That's sort of one end of concreteness. Balmer's at the other end. And then somewhere in the middle is cohomological support variety theories. And that's mostly where I'm going to be talking today, is there. But I'll touch a little bit on the other 2 ends of it. All right, so the basic game, which I'm sure you've seen already earlier this week, is if you have a co-commutative Hopf algebra, you can use that to make a commutative ring and to talk about supports within the spectrum of that ring. So how does that game go? Well, you just take the cohomology ring where you're taking the trivial module for your coefficient, so x between k and k. Okay? And then if you like, you can use the united splice or however you want to think about the product there, but what you get is you get a graded commutative ring, or a commutative ring if you're taking the even parts, which is fine because then the odd stuff will be nilpotent, so it's not going to affect the geometric side of the story. And so then our sort of topological space where everything is going to live will be the spectrum of this ring. But to have a nice theory, you want this thing to be finitely generated, and this is what Chris was talking about, was like, how do you show that this thing is finitely generated? Right? If you believe Pavel and Victor, like if you take any like finite tensor category, it should be, the cohomology ring should be finitely generated, but we don't quite know that yet, unless those guys have done it recently. But so in various cases, we do know that it's true. And so if you do have a finitely generated commutative ring, so it's just a quotient of some polynomial ring, then you can talk about the spectrum of that ring. You can talk about, if you give me a module for A, you can take X with coefficients in M, and thanks to the fact you have this Hopf structure, this thing is naturally then going to be a module over this ring. So then you can talk about the annihilator ideal and talk about the subvariety of the cohomology ring, of the spectrum of the cohomology ring defined by that annihilator ideal. So that's our support variety, and it's right down here at the bottom. So that's sort of the general scheme of the game that is played here. We wanted some geometry. We were using the cohomology to define it, and we're expecting, because it's coming from cohomology, that'll tell us some information about the representation theory. And it's sort of one step away from the cohomology. Like actually computing the cohomology ring or actually computing these cohomology groups can be quite hard in general. Chris kind of alluded to this. And we're sort of avoiding some of that by going to the geometry. So things like nilpotence and stuff we get to ignore. And so places where this sort of started out, if G is a finite group, you can take the group algebra. You could take a restricted enveloping algebra. Or you could take an exterior algebra, and this theory works in a very beautiful way. And lots of people in this room contributed to that in some part, and it's still a very active area of research. All right, so it's kind of where I came into this story is, well, what happened is I became a postdoc at University of Georgia, and my thesis, John Brundon over there, was on Lie super stuff. So I knew about graded stuff, and people at Georgia knew a lot about support varieties. And so we kind of thought about doing both. And so then Vera talked about this a little bit. So there had been some early work in graded stuff, but I think sort of where it started to get taken a little bit further was, I guess this is not classical because it was after my PhD, but still also 20 years ago. Sort of simultaneously, Michel Duflo and Vera did their associated variety, they called it, which was this kind of rank variety that she was talking about. And we did relative cohomology for Lie superalgebras. Now, this is all in the complex setting, which is the first thing you have to learn, is that even over the complex numbers, there's a lot of interesting questions here. And there's lots of things I still don't know how to do there. And we used relative cohomology, and then that brought in sort of invariant theory, because that relative cohomology ring is a ring of invariants. And that led to a bunch of interesting things. And that's not this talk. What I would like to spend my time on is after I was done being a postdoc and became faculty at Oklahoma, I had Chris come and visit, and I twisted his arm because I really wanted to know what was going on in positive characteristic, and we're still trying to figure it out. So that's really where my talk is going to be, is that we're going to be talking about positive characteristic for most of this talk. And so there's sort of a bunch of work in this area now. There's Chris and I. There's BIKP, Benson, Iyengar, Krause, and Petzova. They've done a bunch of valuable work in this area, and various other people have done stuff here as well now. And mostly what I'd just like to do is sort of tell you some of the stuff we know and some of the stuff we don't know, and I think that'll probably, yeah. So I started at 11:30, is that right? So, all right, so yeah, I think that'll definitely take our time. All right, so for now I'm going to talk about odd characteristic. We'll talk a little bit about characteristic 2 at the end. That's actually quite interesting, which I didn't realize for 20 years. It's kind of a baby case, but it's interesting nonetheless. So we're going to have a finite dimensional Lie superalgebra. And so that it's Z2 graded, and we have a Lie bracket, but it satisfies graded versions of the Lie bracket axioms, okay? So there's sort of 2 extreme cases, which are always good to keep in mind, because anything you do should make sense in these cases and should match up somehow with things that are pretty classical. So if the odd part is 0, then you're just talking about a Lie algebra. So whatever is true for ordinary Lie algebras should be true here in the extreme. And in the other extreme, if the even part is 0, then as Vera mentioned, the exterior algebra is what your enveloping algebra is looking like. So again, it should be something you understand quite classically, because you're basically talking about like Kujawa resolutions and things like that. The typical non-extreme case is GLMN, where if you have m plus n by m plus n matrices, the Z2 grading is given by A is m by m, B is m by n, C is n by m, D is n by n, whatever the blocks should be. The grading is given by having the even part be the A and D part, so B and C should be 0. The odd part is the opposite of that. And then you're just taking the graded version of the commutator of matrices. Okay. So in particular, if x was odd, if you had xx here, then you don't get that it's 0, because you have xx plus xx. So there are some differences. All right, so there's a little bit of like what Chris was saying, is some of this is sort of formal nonsense, and at certain points you realize that something complicated has happened. So we're just going to talk about ordinary Lie superalgebra cohomology for the moment. So we're looking at the category of all modules for the Lie superalgebra, or the enveloping algebra, if you like. And so you do have a Cazul complex, and that will compute the cohomology for you. And I should probably emphasize strongly at this moment that even though I wrote exterior, this is in the graded sense, like as Chris has said. When you're taking odd stuff in here, they will anti-anti commute, so things will be commuting. So inside of here, you have, this thing could be written, for example, you could write it as it's the exterior algebra on the even part, tensor, the symmetric algebra on the odd part. So you've got this big, it never stops. You have this big infinite dimensional thing. So for example, if you're talking about ordinary Lie algebra cohomology that's finite dimensional vanishes after some points. You're not really going to get any interesting geometry because all your positive degree stuff is nilpotent, and that won't happen here. Interesting things will happen. So let's see if we can figure out what it looks like. We're in positive characteristic P. So we have a P power map on this subring of polynomials in this thing. And so that P is just a shift according to the grading. And that puts me into S of G1, which, as I just had drawn there a second ago, is inside of this Kujawa complex. And so then that induces a map here of graded superalgebras of this symmetric algebra into here. And it's surjective onto the Pth powers in the target. So the target is finite over this image. So geometrically, what we get from that is that the spectrum that we're interested in is going to be inside the spectrum of this polynomial ring. So it's going to be realizable in a concrete way, thank goodness, inside of G1 bar. Okay. Of course, what is it? That's the question. Well, we've got this map up here, and it's explicit. It's given by these P power maps. You just have to figure out what the kernel is generated by to figure out what kind of relations are being imposed upon you. So that's number one. Number two, if you give me a finite dimensional module for G, I can look at cohomology with X to M, cohomology with coefficients in M dual tensor M, technically, I suppose. And I can think about that as a module using the Hopf structure over the enveloping algebra. And so I can ask, is that a finitely generated module over this cohomology ring? The answer is yes. And then I can define the support variety as we would have before as being the subvariety of the spectrum of the ring, which is this thing right here. So there's some subvariety defined by that annihilator ideal. Okay. And so can we give some concrete description inside of G1 of what this looks like? All right. Well, let me tell you what the answer is. For both of these questions, we can answer it. If you're looking at the first question, what is this spectrum inside of G1? It's this thing that's called the odd null cone. So it's the elements of G1 bar that when you bracket with themselves, you get 0. And as I mentioned deliberately 7 minutes ago, this doesn't automatically happen when you're talking about odd elements. So you're carving out some subvariety there. And one of the things I really like about this is even though we're in positive characteristic and even though we're coming from cohomology, we're being led to, this is the Duflo-Serganova variety if you're in over the complex numbers. So there, for reasons I still don't understand really, there's some mirroring of stories that's happening here.
And this holds for any finite dimensionally superalgebra?
Yes. Yeah. So then what about if I have a finite dimensional module here? Yeah, because all this stuff up here, this is just like algebraic calculations. There's no real structural stuff being used. Well, so this is my cohomological variety, but I can realize it by saying, by some testing of projectivity condition. If you give me an X like this was basically Vera's definition, just reformulated in a slightly different way. I can take the subalgebra generated by it, and I can just ask, is M free or not? And I should emphasize how truly concrete this is because I'm in this situation where X brackets with itself to give me 0. So actually the subalgebra it generates is just spanned by X. I just have, and the enveloping algebra is a exterior algebra on one generator. And projectivity and everything, it's very, very, I've told you everything you need to know. Okay. So with this description of this cohomological variety, I said some properties come pretty easily, like say from the cohomology description, like direct sums becoming unions. Some things like the tensor product are hard from that point of view, but from this point of view, it's like vanishingly trivial.
I'm confused. What if you just took an ordinary restricted Lie algebra?
I'm not doing restricted theory yet. I'll do restricted in a bit.
Relative cohomology as far as that.
Oh, this is this relative cohomology.
No.
No?
No, this is full cohomology for the enveloping algebra, not restricted. For the full enveloping algebra.
Oh,
I see. Full. Despite, okay, fine.
It may not even have a restricted structure.
Yep.
Right,
Yep.
fine.
Yep.
I see.
Yep. We'll do restricted in a little bit. Yeah, so this is totally just some Lie superalgebra you found on the street with no particular structure. So then you get this tensor product property, like I said, basically for free automatically just from this description, because there's not much to say. When you go over this exterior algebra, it's either it's projective, meaning free, or it's trivial and decomposes into direct sums of such, and you're off to the races.
Right. Is a relatively straightforward calculation that this is a variety?
No, I don't.
Another question I can ask is like, is the cohomology ring reduced, for example? So can I actually just calculate the cohomology ring and see what its functions on this thing?
I don't.
Not clear.
Not clear. We don't know what the cohomology ring is for sure.
Oh, okay.
But so I think it probably is easy to see that varieties contained in this cone, because
Yes,
the third
yes.
differential of the spectral sequence already is going to put you on that.
Yes.
But then it's not obvious why it is not smaller than that.
Yes. That's exactly right.
And in this generality, this is always true, right?
So
This
the
is
other
always true,
differentials are
what
not
you
going to
get.
make things much
What is always true?
spectra.
No restriction, no requirements for algebra, any
Yeah.
algebra.
Typically, that's
But
down.
Full cohomology, not like.
The statement
Correct.
is small.
Correct.
After the
I
first
think
differential.
the easy part is showing that
Generally,
it's
it's
at
modular
least this
uniform.
big. The hard part is showing that it's no bigger.
One direction is easy, one direction is hard. I forget.
John, sorry, could you state it in terms of Hopf algebras? Like you take a super Hopf algebra, like rank 1 or something, and then it's Could you state it in terms of Hopf algebras, that you take a certain class of super co-commutative Hopf algebras, and then you
X
get
mod
this?
X squared.
No, are you
Solid.
talking about the enveloping algebra? I mean, we're working with the enveloping algebra. That's your Hopf algebra.
Yeah, but is there a general statement that it's all Hopf algebras?
That look like enveloping algebras?
You mean commutative? Or
Co-commutative.
supercommutative?
Is
Super
there-
co-commutative.
Just for enveloping algebras of finite dimension.
Like primitively generated, it's probably primitively generated co-commutative Hopf algebra.
No, but restricted is not good, right? Because then you will get additional.
No.
Yeah, restricted will be a different story for sure. Yeah. Anyway, this is for us is strictly a thing about finite dimensional Lie superalgebras. Not to say it couldn't be framed in a more general context. So one of the other things, so I'm gonna that I'm gonna mention is classically, by which I use the definition of stuff from before I got my PhD. For finite groups, for example, the dimension, so you expect that these invariants, anything you can say on the geometry side should have some meaning on the representation theory side. So one of them is the dimension of this support variety. That should tell you something about the module. In classically for finite groups, for example, the complexity is giving you the rate of growth of a projective resolution. So the dimensions of a projective resolution and how are they growing. Now here, that's definitely not exactly going to be right because the projectives are going to be infinite dimensional. So whatever this number is measuring for you, it's definitely not that. That's, of course, the most naive thing to try. In particular, though, the dimension will be 0 if and only if the module would be projective. So this is the detecting of projectivity kind of statement. So what can we do with Lie superalgebra? Some of this definitely is nonsensical from the start, but at least this line makes sense. But maybe not exactly, because I just said M being projective would be infinite dimensional, and I already said I was thinking about these support varieties for finite dimensional. So what we did work out, using a really nice result of Avramov and Iyengar, is that if M is a finite dimensional module for a Lie superalgebra, then the support variety will vanish, or so have dimension 0, if and only if the module has finite projective dimension. Okay. So that's what it's telling us about. It's telling us if modules, it's not going to be projective because it's finite dimensional, but it has a finite projective resolution. And just to give you an example of the kind of thing, it's pretty easy to come up with these, because if I take a finite dimensional module for the even part and then induce it up to the entire thing, because the way the enveloping algebra is for Lie superalgebras, that will still be finite dimensional, and that would be something that has finite projective dimension.
And so if it is linearly reductive, and you would consider modules that are semi-simple when restricted to the even part, then it will be the same as projective.
No. No. Projective same dimension.
No, you said projected dimension, but not.
И в категории Frobenius.
I'm taking all modules of the enveloping algebra.
It's different.
It's not going to be projective in that category.
Ah, yeah. Okay.
Of course, yes, of course.
So one thing we get out of this, there's this nice theorem of Bogvad, which says that the global dimension of U of G is 0 if and only if this odd null cone is trivial. So we kind of get a new proof of that. Coming just from this, just specializing this line from up above. All right, so here's in red is the questions I don't know the answer to. So I look forward to hearing them this afternoon.
But can you read them?
So I'll tell you, my handwriting is terrible, I know. I don't know what the dimension of the support variety measures in general. So if it's 0, then we're talking about modules of finite projective dimension. But like if it's 1 or 2 or 3, I don't think you can probably have a good guess at what it is, but I just haven't thought about what it is. But it's certainly not literally complexity for the reasons I said earlier. The other thing I don't know the answer to is this, and Vera sort of alluded to this already in her talk, is I don't know about realization either, because if you do some of the standard tricks like Carlson modules, you're taking a projective module and you're taking some kernel, and the projectives are infinite dimensional, and that kernel will be infinite dimensional, so you're immediately not making the kind of thing that you want. And she said, I did this with Bo and Nakano at a certain point, but we did it in a very ad hoc way for GLMN using parabolic inductions and just working by hand and slowly building up the modules that we needed.
So what does it mean, global dimension 0?
That all modules have, that there's some finite projective. It has a finite projective length. Like,
Maybe it's finite global dimension.
Yeah.
Yeah. Okay.
oh, sorry, finite. Yeah,
Yes.
that's what I mean. Whatever I wrote, ignore that. All modules having finite projective dimension is what I meant to say. So I don't know why I wrote that, but anyway. Yes, and so then we have a variety theory. It has a lot of these nice properties. I also don't know if it's the Balmer spectrum of some nice tensor triangulated category. Here I do have a bit of a conjecture. I think it's the singularity category where you should take the bounded derived category of finite dimensional G modules, mod the complexes of these guys who have finite projective dimension. Because basically the support variety, from that theorem, the support variety theory, you can't see these, so this is kind of in the kernel of that theory, so to speak. And the only thing that really you would need to get something like this is this realization result only. But there's these theorems, like Julia has a version of this theorem, and there's various other sort of theorems which say, here's a checklist of things that you need, all these nice properties, and the main ones that are the hardest ones usually are detecting of the kernel, quote unquote, the projectivity detection, and then realization, and then that tells you that you've got the Balmer spectrum. So
So you said you have the tensor product property?
yes,
Oh, you do, okay.
that's right up here somewhere. So realization, I think, here's the main obstacle to a statement like this. All right, so let's talk about the restricted case. This is a little closer to what Eric is familiar with. Like, we certainly used it very much, Friedlander, Suslin, Friedlander partial as inspiration / I guess in the age of AI, it's okay to rip off from other people now. So we definitely do some of that. So now we're going to say we have a restricted Lie superalgebra, so still finite dimensional Lie superalgebra. What does that mean to be restricted? It means that the G0, it's a Lie algebra, has a restricted structure, so a P power map. And then the adjoint action of G0 on G1 should be a restricted module. So the P action should be compatible in the sense of that line that's in the middle of the screen. And so then what you can do is then you can look at the restricted enveloping algebra, where you take the enveloping algebra and quotient by the ideal given by forcing this equation to be true. So then you're just looking at restricted modules. And then this thing here will be a finite dimensional Hopf superalgebra. And now I'm really in like the case of my second slide, and I can just go to town and see what happens. Oh, I should have said here, maybe I can say in small print, that these x's here, the pth power only makes sense on the even stuff. So this was generated by x in the even part. The odd part already if you take x bracket x, if you think of that as kind of like doing a 2 power, and the fact that x bracket x lands you in the even part, and so the enveloping algebra, you only get powers of 2, it's kind of like already has a 2 restricted structure there on the odd part. Yes. All right, so if we have a, so we can do the restricted Lie algebra, and so if we're looking at one that's a subalgebra, the Lie algebra of some group inside of GLMN, then we have a nice description of what this is, and this was basically on Chris's slides earlier, where R is 1, because when you're talking about the first Frobenius kernel, that's when you're in this situation. And so then you're looking at things that are in G, so something that's even plus something that's odd, so kind of think of them as pairs. And it's this commuting variety, so these two things should commute with each other, and then they should satisfy this equation right here. Okay. And so you can realize it in this particular way. And this is a good place, I think, to pause and to remind ourselves that everything we do here should specialize down to what happens for ordinary restricted Lie algebras. Because if the odd part is 0, then we have 0 here, so we have no beta, it's 0, which means that this thing would be 0, and then we'd just be talking about elements whose pth power is 0. So this is the Pinot-Potent cone, which is what the answer is for restricted Lie algebras. Okay. Good. So what about for a module? Well, so if you take an alpha and beta, what I'd like to do is I would like to have some condition that says, like, I should take M and I should restrict down to the subalgebra generated by alpha plus beta, something like that, but down to that particular element. And sort of a way that make that precise, Pavel brought this up in somebody's talk. I'm losing track of where you asked so many questions, which one's okay with which talk. But you have this algebra that's right here, which we call P1, which it's generated by an even element U and an odd element V, so this relation makes sense. And given an alpha and a beta, you get a map correspondingly from this algebra over into the restricted, this is the restricted enveloping algebra, where U goes to alpha and V goes to beta. And so then the image of it is really just you're looking at the subalgebra generated by that element, right? But it's sort of nicer to think in this way. And so the condition then is you take M, you restrict to the image of that map, and you ask if it has projective dimension 0 for this algebra or not. Okay, so it's in the representation theory of this P1.
So sorry, why can't I use Carlson
Finite
model?
projective dimension.
What?
The restriction should have finite projective dimension, not 0.
Yes. Thank you. Can you say
Why
something?
can't I use Carlson modules for realization in the non-restricted setting?
Because the projective will be infinite dimensional, so the kernel will be an infinite dimensional module. So you won't be. I want to realize them with finite dimensional modules.
Yeah, okay. Oh, it's Carlson module is infinite dimensional.
And so the Carlson modules will be infinite dimensional. All right. And even if this looks a little bit abstract, you can phrase this purely in a rank variety description in terms of the action of the alpha and the beta operators, the two elements, and about what the rank of the matrices are that you're getting. So this, again, is something pretty concrete, even if it doesn't quite look like it yet. And so one corollary of having this concrete description is, again, you can prove the tensor product property. All right, so again, some red stuff, which means things I don't know how to do. Chris can correct me, but I don't think we can do it yet for a general restricted Lie superalgebra. This was only for the case of when we could realize it as the Lie algebra from an algebraic group. So
How do you use it? It's Lie algebra of algebraic in the proof.
because we work first with GLMN and figure out, I don't remember the details of it, but maybe Chris has something useful to say here.
We describe a variety or arbitrary restricted superalgebra.
Is that right?
Why do you need
It was
algebra?
kind of ad hoc to do it.
You need only Lie algebra GLMN.
Oh, no, we described the spectrum, the homology ring, but maybe not the variety. I don't remember.
Yeah, I think the variety for the modules, we use some naturality in that it's inside of, realizing it inside of a GLMN. as a restricted.
I have to look it up.
Yeah, we'll have to
But
look
do
at
you
it.
need, why do you need the group as opposed to Lie algebra? Because you
Well, I
said-
don't need the group. I don't.
But don't you have a Dot theorem that any Lie superalgebra is a Lie algebra of GLMN?
Yes.
As a restricted Lie.
You need restrict. Well, yeah, I think probably also is restricted.
well then-
Because any Lie algebra is a subalgebra of finite dimensional restricted, and that one you can embed. Yeah.
Okay, well, then that answers that.
Actually,
Don't leave it. Because you can
actually, I
just
have to
use-
check. I'm not sure.
Okay, I'm also not sure. The other thing that you'll notice, I claim with this concrete realizations that we would like to be able to compute them, and that's definitely something that needs to be done, is computing these things for interesting modules, CATS modules or simple modules, that kind of thing. Either one of these support variety theories. We haven't done any specific calculations to speak of. We did a bunch of this for the Nakano varieties, where we computed them in specific cases, but in this positive characteristic, I don't know how to, I don't think it's particularly hard with these rank variety descriptions. We just haven't. So if you're a student, that's a good thing to think about. All right, so yeah, so this is good. I may even finish slightly early. The one other thing I want to tell you about is characteristic 2, because this is a case where I thought it was maybe stupid and uninteresting, but you can actually say some kind of cheat and say almost everything once you understand what the definition is. All right, so I'm now going to be working in characteristic 2. So what is a Lie superalgebra in characteristic 2? Well, it's still going to be a Z2 graded thing. The signs don't matter, so now it's a Lie algebra. To be slightly careful, you have to put in the correct collection of axioms so you get all the correct things. Some of these things come for free if your characteristic is like 5 or more. So I'm going to be requiring that if you have an even element, that the X bracket with itself is equal to 0, because that's not going to be for free anymore. And if I have an odd element, then the triple bracket has to be equal to 0. Vera mentioned.
You don't need to do this.
I think
Second one you don't need. It's only in characteristic 3 you need to do this.
Yeah,
Okay.
because
Because 3 times that is a hypothetical.
Yes, no, you're absolutely right. You get a 3 that comes out. In characteristic 3, this one becomes important. That's 100% right. But yeah, what I really wanted to say was in small 2 and 3 characteristics, you have to be actually slightly careful about the axioms, because some of the things are not quite right. The other bit of data that you need is you need to have a quadratic operator from the odd part to the even part, which satisfies these little axioms here. And the way to come to this definition with these axioms is, if you're not in characteristic 2, the thing to do is you take an odd element, you bracket it with itself, so that'll give you an even thing, and you divide by 2. Okay, and so these axioms up here are just encoding what you would expect from that thing, and you're just building it into this definition.
so the universal developing algebra x squared is 0? No.
So if you forget the Z2 grading and this Q operator, and you just have a Lie algebra, then you can talk about the ordinary enveloping algebra of that ordinary Lie algebra. I'm just going to put a bar over it when I'm doing ordinary stuff. No gradings. You just forget the gradings. And so then you have the ordinary enveloping algebra. And then, by definition, if you like, the enveloping algebra here is that mod this extra relation here, which would be just what you expect if it was anything other than characteristic 2, and if this Q was this X bracket X divided by 2. Okay. But then that kind of truncates all the odd stuff. So again, you get this kind of phenomenon where you get the enveloping on the even part tensor and exterior algebra on the odd stuff, at least as a vector space. Okay, so what about it being restricted? Well, if you have a restricted Lie superalgebra, then what did that mean? That meant that the even part had a restricted p power operator, so a 2 power operator. And then it's an easy little lemma which says that if you have a restricted Lie superalgebra, meaning you have this 2 operator on the even part plus this Q map, that you can extend it, I use sort of a curly brace here if you can see, to defining a p power operator on all of G, and so then make it into a restricted Lie algebra in this way. Okay. And then if you've done that, then whether you're thinking about the restricted Lie algebra or the restricted Lie superalgebra, you're led to the same algebra there as algebras. All right. Okay. So I'm doing the restricted version of the story first, and so if I'm thinking about this restricted Lie superalgebra, again, I have this finite dimensional Hopf algebra, superalgebra, and I can talk about the support variety theory and figure out what the spectrum is. And basically what you can do is you can say, oh, look, I can just forget the grading and use this extended version of the bracket, and I now have an ordinary restricted Lie algebra, and then I can look at all the old papers, and it's going to just be the restricted null cone, all elements where the brace of 2 is equal to 0. Yes. But what does the brace of 2 being equal to 0 means? This is the brace of 2 being equal to 0. And if you squint at it a little bit and you think about this Q being the x bracket with x thing, this thing being equal to 0, this one is an even and an odd, so that's odd. This stuff is all even, so the whole thing being equal to 0 means that this is 0 and this is 0. And this is just saying that the even and odd thing commute, and this being equal to 0 is this relation about alpha to the 2 equals, you know, the bracket of beta and beta. So this really, once you pull all the strings off of it, you see that you're getting exactly those conditions that I had earlier in odd characteristic, which is really sort of a nice, beautiful thing to see that that odd stuff, in this sense, is the right generalization, I guess, of the even stuff, because it all coincides at characteristic 2. And again, with the support variety, you can again do the rank variety description, and it's all done in exactly the same way. And the way you can sort of get these results is you can just say, well, forget the gradings, look at what the theory says, and then you see, oh, it just matches because we're in characteristic 2 with what we thought should be true thanks to the odd stuff. Although technically this is not covered by the earlier ones because that was all for odd, but that all matches. So then you get the tensor product property, you get that your modules have finite projective dimension, but here, because we have a finite dimensional Hopf algebra, it means they're actually projective. And we have realizability here because we have a finite dimensional guy now, so I can play Carlson's game for free. Okay. And in this case, and this is, I guess, the last thing I have to say, really, unless there's some questions here at the end, is that in this case, we can actually tell you what the tensor triangulated category you should take to play the Balmer spectrum game to get this variety theory. And again, it's just sort of packing and unpacking definitions. There's nothing too much here. So what do we do is you take the restricted enveloping algebra and you just take the stable category of finite dimensional modules. So finite dimensional modules mod the projectives. Okay, so as you might expect if you're familiar with the theory. And that gives you the Balmer spectrum. And there's only one little wrinkle to it, and that's what this little s is here to remind me to tell you, which is, what do I mean by spec with a little s down below? So this ring right here, so where's the super? There's got to be a little bit of super in there. So this ring right here is actually bi-graded. It's z-graded by cohomological degree, and it also has a z2 grading. So everything is bi-graded. And so when I talk about spec s, I'm taking the bihomogeneous prime ideals. So bihomogeneous ideals which are prime among the bihomogeneous ideals, so using both gradings. Okay. All right, and then if it's not restricted, again, we can kind of chase through things and see what we get, but we get that the cohomological spectrum is the elements of G1 where Q of x is equal to 0, which should be this odd null cone, right? Q is supposed to be x bracket x divided by 2. So this being equal to 0 is what we would have expected it to be, and that is how it comes out. And the same thing with the rank variety description. You take those elements, you restrict to those, and see which one of those are not free. And you get this thing, this finite projective dimension. I did it again. Yeah, that's it.